In module 1, we have learned about the solution of the first order linear differential equation under the category homogeneous, non-homogeneous, exact and non-exact differential equations. In module 2, we will learn about the existence and uniqueness property of the first order linear differential equations. Given a linear differential equations, whether the solution exists, and if the solution exists, how many solutions we will get, whether it is an infinite number of solutions or whether it is no solutions. These are the few questions which we will answer in our module 2. We now look into the existence property of the first order differential equation. We consider the nonlinear differential equation of the form dx dt equal to f tx, x t0 equal to x0, where f is a given function of t and x defined and continuous in some neighborhood of the point t0 x0. Our aim is to construct a suitable function satisfying the differential equation in some neighborhood of t0, and the graph of f contain the point t0 x0. We have also seen that there are initial value problems which have one solution, more than one solution, or no solution at all. Here we want to discuss the conditions under which we can answer these questions. Recall the linear differential equation of the form dx dt plus atx equal to bt. Based on the solution procedure, we can now state an existence and uniqueness theorem for this non-homogeneous linear differential equation as follows. Let the function at and bt be continuous on the interval I a b, and let t0 belongs to I. Then there exists a unique solution x t to the initial value problem 3 satisfying a given initial condition x t0 equal to x0 on the interval I. The above theorem gives the sufficient conditions for existence of a unique solution on the entire interval I where the functions at and bt are continuous. Consider the following example with the differential equation dx dt plus x by t equal to 2, where t is positive, with the initial condition x1 equal to 1. Now, according to the previous theorem 0.1, this differential equation 4 with initial condition 5 will have a unique solution, and we can easily check that solution to be x t equal to t plus 1 by t. In fact, the general solution of the differential equation 4 is given by x t is equal to t plus c by t. Now, please note that the previous theorem says that our at and bt have to be continuous. In this example, the at is 1 by t and bt is 2, which are two continuous functions in the interval 1 and 2. We can observe that the solution of the initial value problem 4 and 5 tends to infinity as t tends to 0. This may not surprise us, as the coefficient 2 by t has a point of discontinuity at t equal to 0. We consider the same differential equation, but with a new initial condition x1 equal to 1 given by equation number 6. Then again, by the previous theorem 0.1, the initial value problem 4 with the initial condition 6 will have a unique solution, and it is given by x t equal to t. Now, this may surprise us, as the solution behaves very nicely at the point t equal to 0. So, we conclude that the solutions of the initial value problems dx dt plus atx equal to bt, x t0 equal to x0 are not necessarily discontinuous at the point where the coefficients are discontinuous. If a solution is not continuous at some points, it is only those points where the coefficients are not continuous. Now, we consider a nonlinear initial value problem 1 to 2, then the situation may quite be different. In general, there is no relation between the region where the function f t x is continuous and the region where the solution exists. Let us take an example where we consider the following nonlinear differential equation of the form dx dt is equal to x square, x 0 equal to x 0, where x 0 is positive, given by equation number 7. If you solve this differential equation, its general equation solution is given by x t equal to minus 1 by t plus c, and the solution of the initial value problem will be given by x t equal to x 0 divided by 1 minus x 0 t. It is to be noted that the nonlinear function x square, since it is a polynomial function, it is continuous for all t belongs to R, but the solution is going to be unbounded at t equal to 1 by x 0, and hence it is valid only in the interval minus infinity to 1 by x 0. So, at this point we may ask the following questions. Number 1, under what condition or what conditions we have one or more than one solutions of the problem 1, 2. Number 2, if it is a solution, whether it is a unique solution or not. And number 3, once we have conditions for existence and uniqueness of the solution of the problem 1, 2, then how can we find the solution analytically or approximately? Consider the scalar differential equation 1 and 2 and ask the existence of a solution x. Example 0.2 shows that any general existence theorem about existence of a nonlinear initial value problem may give assurance only in the small neighborhood of the initial point. So, this problem is a local problem since the existence is described in the neighborhood of t 0 x 0. To deal with this problem, we make certain hypotheses on f in some rectangle centered at t 0 x 0. This will mean that we can apply the local result of this section at every point in a region D in which f satisfies some hypothesis. Suppose f is continuous in D and that t 0 x 0 is an arbitrary point of some domain D. The first step towards the existence result is to show that the initial value problem dx dt equal to f x t 0 equal to x 0 is equivalent to the following integral equation x t is equal to x 0 plus integration t to t 0 f s ds, where t belongs to the interval I. We now prove lemma 1, which says a function x t is a solution of the initial value problem dx dt equal to f x t 0 equal to x 0 on an interval I, if and only if x t is a solution of the integral equation 8 on I. So, the proof goes like this: if x is a solution of dx dt equal to f on I satisfying x t 0 equal to x 0, we have dx dt equal to f given by equation number 9. Integrating 9 from t 0 to t on I, we obtain x t minus x t 0 is equal to integration t to t 0 f s x dx, where t belongs to I, given by equation number 10. Now, imposing the initial condition 2, we see that x satisfies equation 8. Conversely, if x t is a continuous solution of 8, then by the continuity of the function f, the right hand side of 8 is a differential. Hence, by the fundamental theorem of calculus applied to 8, we have that x satisfies the differential equation dx dt equal to f, and putting t equal to t 0 in 8, we have x t 0 equal to x 0, and this ends the proof of lemma 1. With the help of this lemma, we will establish the existence of a solution 1, 2 by proving the existence of a solution 8. So, now our problem is reduced to find a solution of the associated integral equation, that is, now we want to find a function such that it satisfies 8. Now, if we can integrate the right hand side, that is f t x is equal to g t, then we can find the solution of the problem, but in all other cases solution of the integral equation is not so easy to find. Therefore, next we try to approximate the solution of the integral equation. Let us start with the initial condition x 0 as our first guess, that is, we want to check whether x 0 is a solution. The first approximation is given by x 1 t is equal to x 0 plus integration t to t 0 f s ds, t belongs to I. If x 1 t equal to x 0, then x 0 is the solution and we stop the procedure. But if x 1 t is not equal to x 0, then we try to improve our approximation by choosing x 1 t as a better approximation of x t, that is, x 2 is equal to x 0 plus integration t to t 0 f s x 1 ds, given by equation number 12. If x 2 is equal to x 1, then we are done. If not, we proceed further as before. In this way, we can define a sequence of approximate solution as follows: x j plus 1 t equal to x 0 plus integration t to t 0 f s x j ds, where j equal to 0, 1, 2, 3 dot dot dot, given by equation number 13. These approximations x n t are called the successive approximations or Pickard's iterates. We have just learned how to calculate an approximate solution of the differential equation, which we obtained in the form x and t, which are also known as Pickard's iterates. Our next step is to find an interval where these x n's are convergent. In other words, if you plot them graphically, we need to find interval which will contain the graph x and t. If you do that, you will come with a expression which is known as Lipschitz condition. Let us now learn about the Lipschitz condition. We now need to find the interval in which this x and t's of 13 are convergent. In other words, we want to find a rectangle in which the graph of x n will be contained. Let us first assume f and del f del x are continuous function on a closed rectangle R, given by the points t x, where mod of t minus t 0 is less or equal to a, mod of x minus x 0 less or equal to b, centered at t 0 x 0. Thus, the functions f and del f del x are bounded above by constants m positive and k positive respectively, such that mod of f is less or equal to m and mod of del f del x is less or equal to k. Lemma 2: if del f del x is continuous in R and if there exists a positive constant k such that mod of f t x 2 minus f t x 1 is less or equal to k times mod of x 2 minus x 1, Tx1 and Tx2 belongs to R for all point Tx in R. The proof goes like this: if Tx1 and Tx2 are 2 points in R and assume that x1 is greater than x2, then by Rolle's mean value theorem there exists a number eta between x1 and x2 such that ftx2 minus ftx1 is equal to del f del x t eta x2 minus x1. Since the point t eta is also in R, mod of del f del x t eta is less or equal to k, and we obtain mod of ftx2 minus ftx1 is less or equal to k times mod of x2 minus x1, given by equation number 15, valid whenever tx1 and tx2 are in R. Therefore, we come to the definition: a function f that satisfies an inequality of the form 15 for all tx1, tx2 in a region capital R is said to satisfy a Lipschitz condition in capital R, and k is called the Lipschitz constant. The above argument shows that if f and del f del x are continuous on R, then f satisfies a Lipschitz condition in R. However, the converse is not true. That is, there are functions f satisfying the Lipschitz condition in a region, but do not have a continuous partial derivative with respect to x there. For example, if we take f equal to t mod x defined in any region containing 0 0. In our existence result, we need to assume f satisfies a Lipschitz condition in x and not the strong assumption about the continuity of del f del x. In the second example, we take f is equal to x to the power 1 by 3 in the rectangle R of the form Tx, where mod t is less or equal to 1 and mod x is less or equal to 2. Then f does not satisfy a Lipschitz condition in R. To establish this, we need only to produce a suitable pair of points for which 15 fails to hold for any constant k. Let us consider the point Tx1 and T0 with minus 1 less or equal to t less or equal to 1 and x1 greater than 0. Then ftx1 minus ftx0 divided by x1 minus 0 is equal to x1 to the power 1/3 divided by x1, which is equal to x1 to the power minus 2/3. Now, choosing x1 positive sufficiently small, it is clear that k equal to x1 to the power minus 2 by 3 can be made larger than any pre-assigned constant. Therefore, 15 fails to hold for any k. Thus, we have seen there exists some functions f and a region capital R where f does not satisfy the Lipschitz condition. The nonlinear function f is equal to x to the power 1 by 3 may satisfy Lipschitz condition in some other rectangle. For example, if we take R1 equal to some Tx where mod t less or equal to 1 and mod of x minus 2 is less than 1, then we see that f satisfies Lipschitz condition. Here we may observe R1 does not contain T0. Therefore, we do anything with this successive approximation, we must show that they are defined properly. This means in order to define xj on some interval I, we must first know that the point xj remain in the interval R for every s in I. Lemma 3. We define alpha to be the smaller of the positive numbers a and b by m, where m equal to maximum of mod f t and x belongs to capital R. then the successive approximations x j given by 13 are defined on the interval j, which is defined as t such that mod of t minus t 0 is less than alpha, and on this interval mod of x j minus x 0 is less or equal to m mod of t minus t 0 less or equal to b, where z equal to 0, 1, 2 dot 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 given by equation 16. We prove it by mathematical induction. We observe that x 0 is defined on j and satisfies 16 with j equal to 0 on capital J. Now, assume for any j equal to n greater or equal to 1, x n is defined and satisfies 16 on the interval capital J, that is t x n belongs to capital R and the inequality 16 holds. X n plus 1 is defined on the interval capital J as S x n belongs to capital R. To complete the rest of the proof, we need to show that for t belongs to capital J, x n plus 1 t remains in R, or analytically that x n plus 1 satisfies 16 with j equal to n plus 1. But from the induction hypothesis and 13, we have mod of x n plus 1 minus x 0 is equal to mod of integration t to t 0 f s x n ds is less or equal to integration t to t 0 mod of f s x n ds, which is less or equal to m times mod of t minus t 0 less or equal to m alpha less or equal to b, and this completes the proof of this lemma. Theorem 0.2. If f is a continuous function of t and x in a closed and bounded in rectangle R and satisfies the Lipschitz condition in R, then the successive approximations x j given by 13 converges uniformly on the interval j given by t such that mod t minus t 0 less or equal to alpha to a solution x of the differential equation 1 that satisfies the initial condition 2. The proof goes like this. Lemma 3 shows that the successive approximations x j are defined on the interval j. To prove the convergence of the sequence x j on the interval capital J, we write the identity x j is equal to x 0 plus x 1 minus x 0 plus dot dot x j minus x j minus 1, which is equal to x 0 plus summation m equal to 1 to j minus 1 x m plus 1 t minus x m. Clearly, the sequence x j converges if and only if the infinite series summation m equal to 1 to infinity x m plus 1 minus x m converges. The next step is to estimate the difference between x j and x j plus 1. We work on the interval t 0 less or equal to t less or equal to t 0 plus alpha to the right of t 0. We define R j is equal to mod of x j plus 1 minus x j, where j equal to 0, 1, 2 dot dot. Then using the definition 13 and the Lipschitz condition 15, we will get R j equal to mod of x j plus 1 minus x j, which is equal to mod of integration t 0 to t f s x j minus f s x j minus 1 ds, which is less or equal to integration t 0 to t mod of f s x j minus f s x j minus 1 ds, which is less or equal to k times integration t 0 to t mod of x j minus x j minus 1 ds. This you get by using the Lipschitz condition 15, and this is equal to k times integration t 0 to t r j minus 1 ds, j equal to 1 to dot dot dot. For j equal to 0, we have from 14 r 0 t is equal to mod of x 1 minus x 0, which is equal to mod of integration t 0 to t f s x 0 ds, which is less or equal to mod of f s x 0 ds, and which is less or equal to m times t minus t 0, given by equation 18. By using the principle of mathematical induction, we will have r j is less or equal to m times k to the power j t minus t 0 to the power j plus 1 divided by j plus 1 factorial. The case j equal to 0 of 19 is already established. Assume that 19 is true for j equal to p minus 1 for some integer p greater than 1. Then 17 gives, on using the induction hypothesis, r p is less or equal to k integration t 0 to t r p minus 1 ds, which is less or equal to k times integration t 0 to t m k to the power p minus 1 s minus t 0 whole to the power p by p factorial ds, which is equal to m times k to the power p t minus t 0 to the power p plus 1 divided by p plus 1 factorial, which is 19 for j equal to p, and hence this is the proof for 19. Similarly, we can prove the analog of the inequality 19 for the interval t 0 minus alpha less or equal to t less or equal to t 0. Then we have r p is less or equal to m k to the power j mod of t minus t 0 to the power j plus 1 divided by j plus 1 factorial, which is less or equal to m k alpha to the power j plus 1 divided by k into j plus 1 factorial, where j equal to 0, 1, 2 dot dot mod of t minus t 0 less or equal to alpha, given by equation 20. It follows from 20 that the series summation j equal to 0 to infinity r j is dominated on the interval mod t minus t 0 less or equal to alpha by the series of positive constants m by k summation j equal to 0 to infinity k alpha to the power j plus 1 divided by j plus 1 factorial, which converges to m by k e to the power k alpha. By the comparison test, the series summation j equal to 0 to infinity r j uniformly converges on the interval j given by t such that mod of t minus t 0 less or equal to alpha. In view of the definition of r j, this implies the absolute convergence of mod t minus t 0 less or equal to alpha of the series summation j equal to 0 to infinity x j plus 1 minus x j. Since x j equal to x 0 plus summation m equal to 0 to j minus 1 x m plus 1 minus x m, this also proves the convergence of the sequence x j for every t in the interval j to some function t, which we call as x t. Since each x n is a continuous function and converges to x is uniform, therefore, the limit function x t is a continuous function. We will now show that the function x satisfies the integral equation 8 on the interval j. Since x n plus 1 t equal to x 0 plus integration t 0 to t f s x n ds, x t is equal to x 0 plus limit n tends to infinity integration t 0 to t f n x ds. From the uniform convergence of x n to x and the continuity of the function f, we will get x t equal to x 0 plus integration t 0 to t f s x s ds. This proves the existence of the solution x t. Now, under the assumption of the theorem, we can also prove that the solution is unique. Let ut and vt be any two solution of the initial value problem 1, 2, and let phi t is equal to mod of ut minus vt. Then phi t0 equal to 0 and phi t is less or equal to integration t0 to t mod of fs us minus fs vs ds, which is less or equal to k integration t0 to t phi s ds, given by equation 24. We rewrite the last inequality 24 as ddt of e to the power minus k t minus t0 integration t0 to t phi s ds is less or equal to 0, given by 25. Integrating this inequality from t0 to t, we have phi t less or equal to 0, and since phi t greater or equal to 0, this implies phi t is equal to 0, and hence ut is equal to vt for all t belongs to the interval j. Thus, we conclude with the following remarks. Theorem 0.2 is a local existence theorem and discuss the existence only in a small neighborhood of initial point. The proof of the above theorem requires Lipschitz continuity of the nonlinear function even when only existence is required. Regarding the existence of a solution of 1, theorem 0.2 is not the only and the best result. We may have existence of solution without uniqueness. One such important result is stated as follows. Suppose f is continuous on the rectangle R, and suppose mod f t x is less or equal to m for all points t x belongs to R. Then alpha be the smaller of the positive numbers a and b by m. Then there is a solution x of the differential equation 1 that satisfies the initial condition 2 existing on the interval mod t minus t0 less or equal to alpha. Summing up, we have just learned about the existence and the uniqueness property of the first order differential equation. Now, I am sure it is clear, giving a differential equation, you can easily check whether it has a unique solution or more than one solution or no solution. This brings to the end of chapter 2. Thank you.